So going through the practice multiple choice before you take your mock exam. The first question, sorry, I thought the video was running, so there's some stuff written. But we have an object moving to the right with a velocity v, and there's a force F, a force of magnitude F exerted on it. In which of the following situations will the direction of motion change? You want it to change directions, and the kinetic energy to decrease. So let's think about kinetic energy is 1/2 mv squared. Your mass probably isn't changing when you apply a force, so that means it would be your velocity that's decreasing. If your velocity is decreasing to get slower, you would have to have an acceleration in the opposite direction, which means your force, which causes the acceleration, would have to be in the opposite direction to v. Now, I don't want it directly opposite because I don't want it just to slow down. I want it to slow down and also change directions. So here, this one would definitely make it change directions, but it wouldn't make it slow down at all. It would just add an acceleration, add a velocity upwards, so that doesn't make sense. B, this would just make it slow down. It wouldn't make it change directions because it would just start slowing down at the instant shown. It wouldn't turn around just yet, so that's not B. C would be increasing the speed, increasing the kinetic energy because it would be creating an acceleration up and to the right, which would be adding to the velocity here, so that was not correct. Your answer is D, because at this point your force is going against the motion and slowing down, and also making it start to go upwards as well. I guess it's going to be still moving to the right and start to go upwards at that point. Number 2, a ball is suspended by a lightweight string as shown. The ball is displaced in position 1, and released. The 4 labeled positions are evenly spaced along the arc of the motion, meaning like this angle measure equals this angle measure equals this angle measure. And we want to know between which 2 adjacent pairs, meaning like next to, is the change in kinetic energy the greatest. So let's think about when something is falling, the change in kinetic energy, this just comes from the change in potential energy, specifically gravitational potential energy, so I'll call it UG. Potential energy depends on mgh. The mass isn't changing, the acceleration due to gravity isn't changing, but the height is changing. So basically the pair between the pair where it gains the most kinetic energy is just the one that changes by the most height. Now it says that they're evenly spaced, and they are evenly spaced as long as we're talking about like angle and arc length, but as far as height, they're not evenly spaced. So if you go from 1 to 2, this height compared to from 2 to 3, compared to from 3 to 4 right here, obviously 3 to 4 is losing much less height, so it's gaining much less potential energy. 1 to 2 is changing a big amount of height, which means it's losing a lot of potential energy, gaining a lot of potential energy, so between 1 and 2 would be the greatest force. Not the greatest force, the greatest gaining kinetic energy. Number 3, this one is a tough one. So we have a newly discovered planet. It's found to have a density of 2/3 the P, right, density of Earth, has a radius twice that of Earth, where these are the density and radius of Earth. We want to know the surface gravitational field of the planet. So gravitational field is talking about little g. And if you look at your equation sheet, so little g is Fg over m, which is super helpful if you know Fg, but for this specific planet we don't know it. So I'm going to go to the Fg equation, gm1 m2 over r squared. So little g is just this equation, but cross off a mass. So little g is gm over r squared. And we know what's happening to the radius. This is going to be 2 times the radius, which is going to be 1/4 of the force. But we don't know what's happening to the mass. I know something is happening to the mass because my density is changing as well as my radius. So let's look at our density equation. Our density equation actually is given to us. It's this last one right here. See how it's like the curly Greekish P? It also tells you P little thing is density. And then that is mass over volume. So P equals mass over volume. The volume we're talking about of a sphere. So the volume of the sphere depends on, we don't care about like the 4/3 pi, that's just constants. We do care that it depends on the radius cubed, because we just changed the radius by a factor of 2. So that means we'd be changing the volume by a factor of 2 cubed. So it has 2 cubed the volume. We want to know what would happen to the mass in order to get 2/3 the original density, or 2/3 the density of Earth. So I have 2 times the radius, which would be basically 8 times the volume. So 8 times the volume over how many times the mass would give me 2/3 the density. So I'm going to have 2/3 equals blank over 8. Then you cross multiply, so basically we get 16/3 of the mass, and 18/3 of the volume would give me 2/3 of the density. So then up here I have 16/3 of the mass times the 2r squared, so that's over 4. So this gives me 4/3, the original little gravity. Like this. And then I don't want to know just how many times bigger or smaller it is compared to Earth's. I want to know the actual value. Well, Earth's is 9.8, so if you multiply this, you get 13. So here, the trick here was getting how many times bigger the mass is, because once you have that, it's actually pretty easy. Twice the radius, that's a factor of 4. However many times greater the mass is, that goes on top, and then multiply by 9.8 to get your new gravitational field strength. The tricky part here was that I gave you how much of the density changed, which was 2/3. Twice the radius would be 8 times the volume, so you had to use, okay, how many times greater would your mass be if you have 8 times the volume to have 2/3 the density? Alright, number 4. So a bus is initially traveling north at a constant speed. As the bus starts to make a left turn without changing speed, a passenger notices that a box on the floor starts sliding to the right side of the box. Which of the following top views of the box, when correctly labeled, would best represent all of the horizontal forces exerted on the box as it is sliding? So let's cross off C immediately, because it says we're asked for the horizontal forces exerted on the box. There's no force that's causing it to accelerate north, so that doesn't make sense. Now you might be thinking, oh, it starts sliding to the right, so that means there's a force to the right. But let's think about, that is from the perspective of somebody inside of the truck, or whatever, bus. So if you are inside the bus and it looks like it's moving to the right, actually what's happening is that this is turning around like this, which means that we have a centripetal force causing it, because it says it's still at a constant speed, but you can be going at a constant speed and have a centripetal force or centripetal acceleration causing it to move in a circle. So you have a centripetal force in this way. Technically, this would be the friction force between the two. Now, the friction force was not big enough to keep it going in a circle, which is why it started to slide out, so it was B. There's no force causing it to go outwards. So this is a hard one to explain, but think about like when you're driving a car and somebody makes a turn. The turn is to the left, but you feel the force like pushing you outside to the right, to the other side of the car, because what's happening is that the box wasn't actually moving to the right. It was just continuing what it was doing. It was the bus itself that moved to the left that made it look like it went to the right to people inside. Alright, number 5, so which of these takes the longest time to reach the ground? Now if you're going really, really fast, you might be like, ooh, yeah, they all take the same amount of time. That's not true. A and C absolutely take the same amount of time. A velocity to the right does not affect the time it takes to fall down, but B is definitely not taking the same amount of time. Think about this in terms of extremes. Or you don't even have to think about it in terms of extremes, but this one is accelerating down at gravity, negative 9.8 or negative 10 right here. This does not have the acceleration of gravity because it has the normal force pushing up on it. Even if it's frictionless, it doesn't have gravity. So I think about it in the extreme, like, okay, I don't know what this angle is. Let's say it was more like a platform like this. If it looked like this, you would not think that this takes the same amount of time to slide down as something like this. So the one that takes the longest amount of time was actually B. A and C go the fastest because they just have the acceleration of gravity. Here I have just the acceleration mg sine of the angle. So depending on the angle, right, I have more or less acceleration. I'll take more or less time, but it's definitely less time than just g by itself, an angle of 0. Or I guess an angle of 90. Yeah. Which block has the greatest speed just before hitting the ground? This might be another one that if you're going quickly, you're like, oh, sweet, they all start at the same height, so energy is conserved, they all end with the same speed. And they do all start at the same height, but they do not all start with the same energy. So this one starts with all gravitational energy, this one starts with all gravitational, this one starts with gravitational, and it has kinetic at the beginning. It has the mgh, and a 1/2 mv naught squared. So when it gets to the bottom, it's 1/2 mv squared because it will be all, these will all be all kinetic at the bottom. But these two, their kinetic energy is just equal to the potential they started with, whereas this guy is equal to the same potential these started with plus its own kinetic energy. So the greatest speed at the bottom would actually be C. The other way to think about this is like in terms of projectile. You know x and y are separate. These two are going to have the same y velocity when they reach the ground because they're going to be in the air for the same amount of time, accelerating for the same amount of time. This guy, whatever its vy is going to be, this y, the block C will also have vy, but it will in addition have the x velocity as well, which is a greater total velocity. Or I think about it in terms of energy, this one started with more energy than the other two, so it'll end with more energy because energy is conserved. Number 7, so a ball is dropped from rest and it falls to the floor. The initial gravitational potential energy of the ball earth floor system is 10 joules. The energy bounces back up to a height where the gravitational potential energy is 7 joules. So if we think about, okay, right here, I don't know what the height is, but this one had a potential energy of 10 joules. Then it hit the ground, and whenever it bounced back up, now it only has a gravitational potential energy of 7 joules. And it says it bounces up to this height, so it's not like it has also kinetic energy. This is the top. So that means that it lost 3 joules of energy. So let's think about, it probably didn't lose it on its way down. It probably lost it in this collision. So if it's losing energy in the collision, then the energy right after it left the floor, well, that energy has been lost. So that means it's going up with 7 joules of energy. Because we're assuming that it wasn't lost in the fall down or in the path up, it was just lost in this collision right here. So then that means that I have 7 joules of kinetic energy. I come down with 10 joules of kinetic energy because I haven't lost it, it's lost in this collision. So then the mechanical energy, which could be kinetic or potential or both combined, so just like how many joules of either kinetic or potential I have right there, the instant it leaves the floor is 3. How much is lost? Or sorry, circle 3. I said 3. It's 7 joules. I'm losing 3 right here, so I have 10, 10, 10, 10, 10, 10, 10. Lose 3 in the bounce, and then now I have 7, 7, 7, 7, 7, 7, 7. Here it's switching between kinetic energy and gravitational, and vice versa on the way down. But I'm just asking for mechanical energy. All right, number 8, we have a disk initially rotating counterclockwise around a fixed axis with an angular speed omega naught. At t equals 0, 2 forces are shown. If the counterclockwise is positive, which of the following could show the angular velocity of the disk as a function of time? So let's think about, we're looking at velocity. So let's look at the omega at t equals 0. That's called omega naught. And we said that we were going to make counterclockwise, so counterclockwise is going to be positive for us. And the disk is initially rotating counterclockwise. So I have a positive initial angular speed. So the t equals 0 omega or angular speed has to be positive. So I'm going to cross off A and B because those start with a negative angular speed beginning. And I started with a positive. Told me it should be positive. So now I'm just between C and D. So let's think about, now I need to know what's happening to the omega after it's released, after t equals 0. These two have two different forces, and you might be like, oh, they're both down. But when we're talking about angular velocity, I care about the direction of angular acceleration, which isn't from a force, it's from a torque. So here, this would be counterclockwise, and then this one would cause a rotation around clockwise. So this would be a negative torque, and this one would be a positive torque. Now, it's not exactly 40 newtons and 20 newtons, right? We would need to multiply, but I can tell that this is a bigger torque, so my net torque on the object is going to be counterclockwise. So that means I have a negative net torque on the object, which means I have a negative angular acceleration. So that means that if I start with a positive velocity and have a negative acceleration, then it should be decreasing. And whenever it gets to 0, it's not going to turn around and have a torque the other way all of a sudden. It's going to continue on because it has constant torques, constant forces, constant torques, constant acceleration. So this would be super, super similar to if I asked for a velocity versus time graph. If I said it starts moving to the right and then I gave you just like, let's say I gave you 40 newtons and 20 newtons and 40 newtons, and I said that it started off with a velocity v naught this way. Well, we would say, okay, my acceleration is this direction right here. That's a negative acceleration. I start with a positive velocity. Well, I start with a positive velocity, but that is going to decrease. That would be the linear equivalent of this rotational rhythm. A 50 Newton box is at rest on a horizontal surface. The coefficient of static friction between the box and the surface is 0.5. The coefficient of kinetic friction is 0.3. A horizontal 20 Newton force is then exerted on the box. The magnitude of the acceleration is, so free body diagram, 50 newtons is the weight. I do not need to multiply by 10 or 9.8 here because it already is given as a force, not as the mass in kilograms. It's rest on horizontal surface, so my normal force is also 50 newtons. And then I have a horizontal force, so horizontal, I'll call it an applied force of 20 newtons. So this 20 newtons is only going to accelerate if at first I overcome the static friction, because it says I'm starting at rest. So I need to know what is the maximum static friction that this box and this surface will have, because I need to overcome that. So I'm going to use static friction, coefficient 0.5, normal force 50. That is a 25 Newton force. So if my maximum static friction is 25 newtons and I push it with 20 newtons, then this applied force is not enough to overcome the static friction, so it's not going to move. It won't move. One mistake I would maybe guess that someone might make is they would say, oh, static friction, that's 25 newtons. And then they'd be like, oh, that's a net force of 5. Mass divided by, or net force divided by mass, that gives me an acceleration of 1. What's wrong here is that static friction is actually a less than or equal to, I have to think about the less than or greater than each time, less than or equal to the mu Fn. So if I'm pushing it at 20, I actually don't have a static or a force of friction of 25. This is only going to push back at 20. It will just go up until, so it'll be less than the actual value until I actually get to 25. Then it'll push back with 25. And then after 25, then it'll be moving and it'll be kinetic friction. So we have to be super careful with static friction. You can have less than the mu Fn for static friction for sure. Number 10, a thin rod of length d is on a frictionless surface, pivoted about one end. As shown, it can rotate freely. The rod is at rest when it is struck by a sphere with linear momentum of magnitude and pi, like initial momentum, perpendicular to the rod. The sphere rebounds along its original line of motion with momentum of magnitude pf. What is the magnitude of the angular momentum of the rod immediately after the collision? Alright, so we are talking about a collision. It's not just linear momentum, we're talking about angular momentum, so I'm going to use conservation of angular momentum. So basically, your L, angular momentum, so L of the, what did they call it, a sphere, L of the sphere before is going to equal L of the sphere after, plus L of the rod after. The reason I don't have L of the rod right here, you can, but it's just 0 because at first the rod isn't moving. So then now I just need to figure out, I've been given the linear momentum, but linear momentum is not the same as angular momentum. In fact, we have learned that for something moving in a straight line towards a pivot point, this depends on the mass and how fast it's going and how far from the pivot point it is. Because if I hit at this point right here, that is very little angular momentum, very little torque compared to if I hit it right here. So the angular momentum, if you remember, for something moving in a straight line is mvr. So here I have to relate that to pi. Well, pi is just mass times velocity. So the angular momentum of the sphere beforehand is just pi times the distance r, which in this case the distance r is actually a distance d. Okay, and then the angular momentum afterwards would be, of course, mvr. Now my mv is this pf, and my r, the distance to the pivot point, is still d. What I need to be careful with here is I just changed directions. Instead of going counterclockwise, now this is like a clockwise angular momentum, so I need to be careful with the sign here. So my sphere before we said was PID. My sphere after is negative PFD, because that's like my MV after, plus the L of the rod. I'm trying to solve for L of the rod, so I'm just going to add this over. I have PID plus PFD. And then if I factor out the D, there's just PF plus PI times D. You get C if you didn't pay attention that this would be in opposite direction. So actually the change here, right, is like this minus, or not minus, plus that value. Okay. Alright, a spacecraft is placed in a circular orbit around a planet with mass this. So this is the mass of the planet. And then this spacecraft orbits at a height above the surface. And I want to know what else I need to know in order to calculate the speed of the orbit. So orbital speed, we should just have this in our head memorized, square root of gm over r. So the mass, remember the mass that we care about is the mass of the thing it's orbiting around. We don't care about the mass of the spacecraft, so we definitely don't want mass of the spacecraft. That's irrelevant. We just want mass of the planet, which we already know. We already know this, so check and check. We need the radius. Now it's tempting to be like, sweet, I have the radius, but actually what you have right here is the height above the surface. So, I already have diagram, whatever. This distance right here. For r, you need to go from the center all the way to the center of the of the object. So you would need to add in the planet's radius, so that is why the answer choice is B, because what you have is just like the height above the surface. You need to know the distance to the center in order to have the full R. So B was your answer. 12 two carts of mass 2m and m approach each other head on. They both start with the same velocity. When they collide, they hook up together, so they get stuck together. Which of the following best represents the momentum of the cart M as a function of time before and after? So we're looking at cart M. At first, it's moving to the left, and velocity and momentum absolutely has direction. So I should start with a negative velocity or negative momentum. And then when they hit, they're going to stick together. This one has more mass with the same velocity, so it'll have more momentum than the other guy, so they'll get stuck. When they stick together, they'll end up going to this side. Now, this one is going to give some of its momentum to the smaller mass cart in order to turn it around and get it moving the opposite direction. So whatever velocity they're going off with, it's going to be less than v. Because this guy's coming in with v, but then it's giving some of its momentum away to turn him around and go to the right. So I want to know, and then if this one's going, if this one gives some of its momentum away and is going less than v, then m is now going less than v, obviously, because they're stuck together. So I have a negative momentum, and it goes to a positive momentum, and it's going to be slower, less momentum than before. So we can cross off A and B, because they don't